everyone, I'm Alan. Today I want to talk about some properties of unitary operator in quantum mechanics. So let's get started. So when it comes to unitary operation, we deal with two kinds of problem. There is a spatial translation and time evolution. Before going to prove some claim, we have to know some property of unitary operators. So property 1, we have the inverse of the unitary operator that is equal to the dagger of that. So we can work in this way. We have the unitary operator with the ij in the matrix form. When we dagger it, so what we expect to have is a complex conjugate. The second property is that when the inverse times itself, the unitary times the inverse, that is equal to the identity operator. The third one is that this is dagger of the unitary operator times the unitary, which is equal to the dagger times the unitary, that's equal to the identity operator. And we come to the fourth property, that is A, B dagger is equal to B dagger, A dagger. The inverse of the unitary, that is equal to the dagger. And we have V as another operator. The inverse is equal to the V dagger. We combine them together to form an operator. So UV as an operator. Now we come to our first claim. So the claim is that the product of the unitary operator is an operator. The proof is as follows. We have UV as an operator, dagger times UV, that is equal to V dagger U dagger times UV, and that is, we can see that U dagger times U, that is equal to I. So we have V dagger V, and these two also an identity operator. So we finally have I as an operator. So that is the proof. Now we come to the second claim regarding the eigenvalue equation. That is, the magnitude of the eigenvalue of the unitary operator is equal to 1. So claim 2, magnitude of eigenvalue of unitary operator is 1. We can express this in equation. So that is our eigenvalue lambda. So we square it, that is equal to 1. So we expect that lambda is equal to 1. So how can we get to this result? Now we have unitary operator acting on the eigenstate lambda, which gives out the eigenvalue lambda times eigenvalue lambda. The proof is as follows. So we focus on two perspectives. One is the unitary, another one is the eigenvalue. In the unitary part, we have the operator acting on a state, and then we scale it. We get this magnitude lambda U dagger U acting on lambda square, and now we have lambda and lambda star because of this dagger acting on the bra and this unitary acting on the eigenstate. We have lambda eigenstate, so that is lambda square lambda lambda square, so that is lambda square in the eigenvalue perspective. And now we have the unitary operator acting on the state. It's squaring it, the bra lambda dagger, and now we have the bra vector acted by the dagger times U acting on the eigenstate, squaring it, and because these two is equal to I, so we have the inner product of lambda, which is 1. So when we equate them together, we get lambda square is equal to 1. And that's how we get lambda is equal to 1. And what else can we observe from this phenomenon is that lambda can be expressed as an exponential value. So lambda is equal to e to the power of I psi to the order of lambda, and psi to the order of lambda is a real number, and because this exponential is equal to 1, so we can express this real number can be any form. And the unitary operator is correspond to the eigenvalue, that is a complex number, while the Hermitian operator correspond to the eigenvalue, that is a real number. And both the magnitude are equal to 1. The unitary operator acting on the eigenstate, that is the eigenvalues times the eigenstate. And then what we can expect that the bra vector is acted by the unitary operator that gives out the eigenvalue of the bra vector. So unitary operator acting on the state, eigenstate, that's equal to the lambda. So the proof is as follows. We have lambda, and that's equal to the identity times lambda. And we know that identity can be expressed as the unitary times the dagger itself. And the unitary operator acting on the eigenstate, which gives out the eigenvalue, lambda, and the unitary dagger acting on the lambda. And now we express lambda as an exponential form. So e to the I sine lambda u dagger lambda. Now I want to make these as a subject of the equation. And now we have u dagger lambda is equal to e to the negative I sine lambda times lambda. And then I will change it to the bra vector form, bra lambda times u. And this exponential can be expressed as lambda star times lambda eigenvector. So the bra lambda times the u dagger, which is equal to the lambda eigenvalue times the bra vector lambda. And then I will come to our claim 4. The claim 4 is that the eigenvector corresponding to the different eigenvalues, they are orthogonal to each other. Eigenvector correspond to different eigenvalue is orthogonal. U times lambda, it gives out lambda, right? This is the first one. And the second one is the u mu gives out mu. And we can express this as the bra vector form. So now we have the bra vector acted by the unitary operator gives out the eigenvalue mu times the bra vector mu. And this deduction is from the claim 3. Now we sandwich the unitary operator by mu and lambda. So bra mu and lambda. Now we have the unitary operator acting on the eigenvector. So we have mu lambda, and the number can be taken out. So now we have an inner product of mu and lambda. In another way of the action of the unitary operator, we have mu u lambda, and now acting on the bra vector, we have mu lambda, and number can be taken out. So we have mu lambda as the inner product. So because they are equal to each other, now we subtract them together, so we have lambda minus mu times the inner product of mu of lambda, which is equal to 0. So if lambda is not equal to mu, we expect to have the inner product equal to 0. So it means that if we have the state with different eigenvalue, they should be orthogonal to each other. So that's it for today's introduction. I will go through more about the unitary operator in another video, so please like, share and subscribe my channel to get any updates about my videos. So see you later. Ciao.